This short video is about the pseudorandom permutation security notion for a function family, or PRP for short. It's a pretty simple notion, and it, along with the closely related pseudorandom function, or PRF, security notion, are the two that we will use most often, I guess throughout the course, but certainly when talking about function family, these are the two notions that we'll use the most. And the reason that that's the case is they're extraordinarily useful. So we'll find that if you have a function family, so if you want to be concrete, think about a block cipher, that is assumed to be secure as a pseudorandom permutation or as a pseudorandom function, that will suffice to allow us to prove things like counter mode is IND-CPA secure. So they're very useful notions. And another way in which they exhibit their power, other than the ability to support the construction, the provable security of sort of higher level constructions like encryption schemes, is that they also imply lots of other security properties that one might try to formalize for a function family. So, for example, you've already seen a video on key recovery as a security notion, where there the adversary is interacting with the function family with a secret key. It's asking inputs, it's seeing outputs that have been computed by the function under that secret key, and at the end it tries to guess what the secret key is. Well, it's not hard to show, and in fact I think I'll post another video that shows that in fact the PRP and PRF notions suffice to also give you key recovery security. So, to try to say that more clearly, it's not hard to show that if you have a function family which is secure in the PRP or PRF sense, then that function family is also secure in the key recovery sense, meaning you can't recover the key. Yeah. So let's, and I should say, and also lots and lots and lots of other notions, essentially any notion you could come up with for a function family, any security notion you could come up with, it will end up being implied by security as a PRP or as a PRF. And so in some sense, the PRP and PRF security notions are the master notions for function families. So let's get into this. We'll talk about this a bit during in-class lecture as well, but I wanted to at least have this video available to you so that you could look at it in your own time and refer back to it when needed for homework sets. So to get things started, we have to we're going to fix a function family. I don't care what it is. It doesn't necessarily need to be invertible even, but just some function family that takes keys from some set calligraphic K, which up here we're saying is non-empty, which is important because otherwise you don't have a function family. And it takes an n-bit string as an input and it outputs an n-bit string, where n is some integer that's greater than 0. So this is sort of the formalities of getting started. So we have this function family, and if you think of this function family as being a block cipher, say, then we know a block cipher is a permutation for every key. If the block size is n bits, so using this particular function family as an example, if f is a block cipher, then that means for every key k that's in the set calligraphic K, the mapping f sub k is a permutation on n-bit strings. So in a sense, the best possible behavior that you could hope for from a permutation is that it behave like a uniformly sampled permutation from the set of all permutations. When we sample a permutation uniformly from the set, we typically refer to it as a random permutation. The permutation itself isn't random in its own behavior. It's random in the sense that it was sampled randomly from the set of all possible permutations. Of course, once the permutation is sampled, its behavior is completely determined. Yeah, it's deterministic at that point. But it's very intuitive that the best possible behavior, the ideal version of a secretly keyed block cipher, is a random permutation. You can't hope to have a better block cipher in some sense than one that when you pick a key at random and you keep it secret, its behavior is indistinguishable from that of a random permutation. And that's what this PRP experiment captures. So let's just walk through it. As usual, we have the name of the experiment, which is capturing the PRP game, pseudo-random permutation game, for the function family f that we've just fixed, and some adversary A. And again, we use this A here as kind of a generic placeholder, but when you are trying to build a tax, for example, we always mean a specific A here. Yeah. So this is some adversary A playing this game, and the game proceeds as follows. The first thing that happens is we pick a bit at random. This will be the challenge bit for the game. Then we pick a key from the set of keys for the function. Then we pick a permutation, pi, uniformly from the set of permutations on n-bit strings, where n is exactly this value here. So this makes sure that f sub k and the permutation pi will be mapping on the same sets. Then we run the adversary A, that's named in the experiment, with an oracle O whose behavior is specified over here. At the end of its execution, it outputs a bit b prime, and as usual for bit guessing games, we return the truth value of whether or not b prime equals b. It's the oracle whose behavior depends on this challenge bit b. In particular, when the adversary asks the oracle some n-bit string x, here x is again just kind of a generic placeholder. It's like whenever you ask something, this oracle takes this input, let's call it x. If the bit b is equal to 1, then we run the function with the secret key k that was sampled on that input x and assign the value to y. Otherwise, when the bit's equal to 0, we instead apply this randomly sampled permutation to the input x and assign that value to y, and then we return that value y. So in effect, I've got a picture over here. The adversary is running with this oracle. It can ask a value x to the oracle. If the bit in that oracle is 1, then it's going to return f sub k of x. If the bit in that oracle is 0, it's going to return pi of x. Yeah? And the adversary can make as many queries as it likes. It makes these queries adaptively, as we've talked about in our previous security notions, in the sense that, A can run some computations, it can flip coins, and then it comes up with the first query x it wants to ask, and it gets back the response. And then based on that response, it can now do more computations and flip coins and then decide on a second query x to ask and get that response, and so on. At the end of its execution, it outputs a bit b prime. Yeah? So this is a graphical depiction of the experiment over here. It's a pretty simple experiment, and it's capturing this idea that if you are unable, if an adversary A is unable to guess the value of the challenge bit with probability significantly better than a half, because a half is always possible when you're guessing a random bit, then we say, well, A cannot distinguish between f sub k and a random permutation, which means from the perspective of that adversary, any use of f sub k, whether that be inside of an encryption scheme or any other construction we might build from the function family, in any place where f sub k is used, from the perspective of the adversary A, it's as if a random permutation was being used instead. So, and that's really the power that we're going to leverage when we start looking at the provable security of encryption schemes and other things that are built from block ciphers and more generally from function families. We're going to leverage this power that if I can argue that no efficient adversary A can distinguish the behavior of f sub k for a secret key k from that of a random permutation, then any place that f sub k is used, I can pretend like it was instead a random permutation that was being used. And that allows us to analyze higher level constructions kind of in this idealized setting where the secretly keyed block cipher function, whatever it is, has been replaced by a random permutation. Okay, so moving on in the usual way, we have this experiment, and then we have to define the advantage of A. And we just said a moment ago that any adversary A, there's always an adversary that gets probability half of winning this game. For example, the adversary that simply outputs 1 without asking any oracle queries, that gets probability a half of guessing the bit. So to define the PRP advantage of A against this function family F, we take the probability that the adversary causes the experiment to output 1, which means that the adversary guesses correctly the challenge bit. We take the probability of that event, we multiply by 2 and we subtract 1, so that the advantage itself will now always fall between 0 for the worst adversaries and 1 for the best possible adversary. If you look at this experiment, you can imagine that if I allowed an adversary A to run for an exponential number of steps, then it could do an exhaustive key search. So, for example, it could ask a query X and get back a response Y, and if the bit in the oracle is 1, then it could sit offline and carry out an exhaustive key search, trying every key K that's in this set calligraphic K, running that F sub K on the value of X that it asked to the oracle, and seeing whether or not its local computation of F sub K matches the value Y that was returned. If you do an exhaustive key search like that, well, a little bit of work will convince you that the probability that you'd be fooled by a random permutation into thinking that you found the right key when there really isn't a key because it's a random permutation, the probability of that happening is very small. And so an exhaustive key search attack is almost always going to win this experiment. But that requires that A run an exponential time. So we're definitely going to want to track as one of the resources the time complexity of the attack, the number of computational steps with respect to some implicit underlying model of computation. So we're going to track the running time because you would expect that as the running time of A goes up, the probability of it winning this game is going to get better. We'll also track, as usual, the query complexity, or the number of queries that an adversary A asks of its oracle in its attack. And here again, we have the intuition that if you allow me to make lots and lots of queries, then I'm much more likely to be able to distinguish the behavior of the true function family. Yeah, this is some algorithm that's been keyed. If you let me ask, say, all of the points X that are in the domain of F sub K, then you'll know the entire mapping of your oracle, and you'll be able to then carry out an attack where you can determine with very high probability that you in fact have one of these. So, for example, if you tried all the keys and you checked this entire table, then you'd know exactly whether or not for any key K, the table corresponding to F sub K matches the table that you got by asking every domain point of the oracle. So, just like in the case of time complexity, if the query complexity is allowed to be arbitrarily large, then we also expect that it'll be easy to win this game. So we're going to track the time complexity and the query complexity of any attack. We're not going to track the total length of the queries. Now, we could do that, and that would be fine, but here it's not as important because the domain is fixed length strings. So we know what the length of queries is. If you ask Q queries of the oracle, then the total length of the queries is Q times N. For fixed length input and fixed length output function families, typically won't track the length of the total bit length of queries because you could compute it immediately anyway. It would be a different thing, right? If the domain of this function were 0, 1 star, for example, then it may be important to track the length of the inputs because the inputs can vary in length. And maybe you're asking lots of short inputs, or maybe you're asking a few long inputs. In those cases, it's more important to track. But when the domain is a fixed size input, in this case n-bit strings, and the range is fixed sized as well, then not only could we immediately compute from the number of queries what the total bit length is, but in some sense it's unnecessary because if you think about, say, building an encryption scheme out of F sub K, with one query, to this thing, you only get one piece of information in a sense, right? You only get one block of information, not multiple blocks. So anyway, these are the two resources we're going to track in the PRP experiment. And as before, we're going to define a resource parameterized version of this advantage. This advantage in the PRP experiment against F with resources T and Q, right? This is the resource parameterized version of this advantage. And as before, this is defined to be the maximum over all adversaries that use resources T and Q of their advantage. Yeah, it's the best possible advantage that any adversary A that runs in T steps and asks Q queries can have. And informally, we will say this over and over again in the class. Formally, we say F is a good PRP or it's a secure PRP if this advantage is small, which is in quotes, for all reasonable values of T and Q. Yeah. So in other words, reasonable values of T and Q is saying like for all efficient attacks. And as we talked about in one of the previous in-class lectures, we put these terms in quotes because they are informal, right? What small means is really kind of up to you. Likewise, what reasonable values of T and Q are, again, is very application specific. It's context dependent. For small probability of distinguishing F sub k from a random permutation, in some applications maybe 2 to the minus 80, in other ones it might be 2 to the minus 40. It really depends on what kind of security your application demands. And closely related is what a reasonable length running time of an attack is and what a reasonable number of queries that you're going to allow. That also depends heavily on the application. So this is the PRP, pseudo-random permutation security notion, and we'll be using this over and over again in class. So I'm going to post separately a video that talks about the closely related PRF notion, and we'll actually get to use it a little bit, and we'll see, in fact, how it relates, formally speaking, to the PRP notion.